So let's discuss operators. So when we discuss Verilog operators, it's important to see which operator is used for which hardware. So synthesis, keep synthesis in mind when you learn operators. So first let's look at bitwise operators. So these bitwise operators work on each bit of your wire, right? Okay, so let's say if our A is a wire, let's also add B and C to it. So A, B, C are wires, and let's have some buses, say 4-bit buses, and let's call them W, X, Y, right? So this should help us learn how operators work. So let's pick up NOT operator. So the symbol for NOT operator is tilde. So we're going to say A is equal to tilde B. So when you say A is equal to tilde B, now B gets inverted and flows to A. So that is how we see. So B gets inverted and flows to A, right? So this is the hardware that you'll get if you use this tilde operator, right? So you have one operand, and before the operand you put tilde and you get A, right? We can also say X is equal to, say, tilde Y. So Y gets inverted and becomes X. So Y gets inverted and becomes X. And just that, since X is a 4-bit and Y is a 4-bit, so you cross it and write 4. That means this line is a 4-bit line. It's not a 1-bit line like this one. So if expanded, it will look like this. So you have, say, Y of 0 with a single NOT gate to X of 0 and so on till Y of 3 with a single NOT gate to X of 3, right? So you have 4 NOT gates totally, right? Next, let us look at bitwise AND. So we'll keep this, we'll remember this. A, B, C are a single bit, W, X, Y are 4-bit each, right? So we'll use them as we go, right? So bitwise AND. So bitwise AND, this is the symbol. Let me write NOT gate, this is a symbol, right? So when we say A is equal to B and C, right? So this means that C and B are ANDed and the output is A. So you get this structure when you synthesize this line, right? A is your output, all a single bit. Now when you say X is equal to W and Y, so W and Y are ANDed together and you get X. Now all of them are 4-bit wide. This just means that there are 4 2-input AND gates, right? Okay. Next is OR gate. So OR gate has the symbol thus. So when we write A is equal to B or C, C is ORed with B and gets A. So it's like this. So C, B, and you get A. Now if I write X is equal to W ORed with Y, then you get X as output, W and Y, but both are 4-bit, and X also, right? So you have 4 OR gates, 2 input OR gates, right? Next we'll see XOR. XOR has this symbol cap, right? So A is equal to B XOR C. So you have C and B, they both are XORed, and you get A, and all of them are single bit, right? So if we write X is equal to W XOR Y, then Y and W both are 4-bit, and you XOR and get X is also 4-bit, right? Then let's see XNOR. XNOR can be this or the other way around, but this is the issued convention, right? So A is equal to B XNOR C. So then we get C B XNOR and A, both are single bit, and X is equal to W XNOR Y. The same way, W Y 4-bit each is XNORed, and you get 4-bit X. You have 4 2-input XNOR gates, right? And the NOR gate, so NOR gate is again tilde OR, and A is equal to B NOR with C gives B and C, NOR with each other, and you get A, right? And for a bus, W NOR Y, you get W Y 4-bit each, and NOR gate and 4-bit X, right? And NAND gate is tilde and A is equal to B tilde and C. That gives you B, C, and NAND and A. When we use buses, we have X is equal to W and NAND Y. So W and Y are both 4-bit, X is also 4-bit, right? So these are the gates. So all these gates are synthesizable. That means that you can convert all of them into hardware, right? So they're all direct bitwise gates, and each of these symbols have a gate as their synthesized block. So let me quickly remind you the uses of each of these gates. So a NOT gate is used to complement, right? So if you want to complement bits, say you have 1 1 0 1 and you want to take a complement of this, that is when you will use NOT gate, right? An AND gate is used for masking bits. Say you have 1 1 0 0 and you want to say extract only these 2 bits and you want to leave out these 2 bits. So then you will AND with the value 0 1 1 0. So this will act as a filter. So you remove the extreme bits and you get the in-between bits as it is. So this is one way to use an AND gate, that is to mask bits. And the other purpose of AND gate is to force reset something. Say you have a control register and you want to set a certain bit of the control register to 0. Say if your previous value of your control register is this and you want to reset only this bit, then you would AND with a value 1101. So when you AND with the value, all these bits will be copied as it is except this bit. This bit will be resetted. So you will get 1011. So whatever is the value, the previous value of the control register will be copied as it is, except this bit will be forced reset. So these two are main uses of AND gate. And OR gate will also help in masking bits, but if you want the bits to be filled with ones instead of zeros, you can use OR gate. So say for example you have 0 1 1 0 and you want to extract these two bits, then you can OR it with 1 0 0 1. So you are trying to extract these two bits and fill the rest of the bits with the value 1. So then you will get 1 1 1 1. So these are the rest of the bits and these are the bits that you have filtered out, right? So you want to fill the rest of the bits with 1 and extract certain bits, then you can use this filter and OR, right? The most important purpose of using a OR gate is to force set a value. So say for example you have the control register as like this 0010 and you want to set this bit. You want to set only this bit without disturbing other bits. Then all that you have to do is OR with the value this. So you can set this bit. So you'll get 1 1 0 0. So this bit was 0. Now it has become 1. So this probably is the most important use of an OR gate. An XOR gate is used to selectively complement certain bits. Say for example you have 0 1 0 1 and you want to complement these two bits. So if you want to complement these two bits, you put a 1 in these two bits and a 0 in others. So you will get 1 and this bit, since it is XOR 0 with 1, you'll get 1 and 1 and 1 you're going to get 0 and this is going to be 0. So these two bits have remained the same and these two bits are complemented. So you want to complement certain bits selectively, then you would prefer to use XOR. XNOR is used for bit pattern matching. So say for example you have 0 1 0 1 and you want to match certain bits. So you want to check if that's a match. So you want to say match these two bits or all the 4 bits. Say let's say we want to match these two bits. Say you got a certain value, say 0 1 0 0, and when you check for a match you're going to get 1 1 here and this is what you're looking for. And since this is also a match, you're going to get a 1 here. This is not a match, so you're going to get a 0 here. So the bits that end up being 1, so those bits are bit positions are a match. And where you get a 0, those bits have not matched. So that is the use of XNOR. NOR gate is going to do two things. It is going to force 0 and as well as flip bits. So it can do two things. So let's see. Let's take an example, say 10101, and say we want to force 0 in these two positions and flip these two positions. So if you want to flip, you put them as 0. If you want to force a 0, you put the bits as 1. So you see, so this is 1 and 0, you get a 0, and this is the extreme positions are 0 and 0, so you get 1, and so these two have flipped, and we're going to force a 0 in these two places. So since these two are 1, so your NOR gate output is going to be 0, right? So you can force a 0 as well as flip bits. With NAND gate, you can do slightly different thing. You can force 1 and flip bits. So let's take the same example, 0 1 0 1, and you want to force a 1 on these bits, so you put a 0 0 in these positions, and you want to flip these two outer bits, so you put a 1, right? So since these two are the extreme, LSB bit is 1 1 1 gives you 0, and this MSB bit 0 1 gives you 1, right? So you flipped these two bits, and you want to force 1 on these two positions, you put a 0, and you get 1 here and a 1 here, right? So you've forced the 1 in these two positions and flipped these extreme positions. So remembering these purposes of different gates can help us design more efficiently, more purposeful design when we use logic gates.